So here we'll look at an example of a problem that you probably saw before in some math class that you took before calculus, involving half-life. So let's see if we can kind of derive this equation from the ground up. Let's just first define what a half-life is. Half-life is the time required for half the material present to decay. So I'm going to write that it's the time required for exactly half of the material present in a sample to decay. All right, so these half-life problems always are always modeled by an exponential function, and the reason is because the rate at which the amount of carbon in this case is decaying is going to be proportional to the amount present. Now, we're not going to resolve the differential equation. We're going to take it on faith that it's going to have this structure here. Right, that should be the solution to a differential equation involving half-life. Now, if we're told that 5,700 years is the half-life, what that means is that after 1,500 years, or 5,700 years, so after 5,700 years, exactly half of the initial amount will have decayed. Which means that half the initial amount will be present. So we can use that fact to actually find, there's a couple of unknowns in this problem we're going to need. We're going to need the y sub 0 and we're going to need the k. But if after 1,500 years, or I keep saying that, 5,700 years, half the initial amount will have decayed, that means there'll be half left. So that means I can write this. I can say 1/2 of the amount present at the initially is going to be equal to the initial amount times e to the, now our k value is what we don't know, but we know that this all happens after 5,700 years. And you'll see that these cancel, and we end up getting that 1/2 is equal to e to the 5,700k. And if we take the natural log of both sides, seeing how ln and e are inverses, this turns into ln of 1/2 is equal to 5,700k. And solving for k, that means that k equals ln of 1/2 divided by 5,700. So we've solved for our k. One thing that you might want to note is that in general, that 5,700 is just the half-life. So if I solve this for the half-life, 5,700, that equals ln of 1/2 divided by k. And so in general, what this says is that the half-life is always going to be natural log of 1/2 divided by that k value. Alright, so that's just one. I don't even know if it's worth remembering, but I guess if you come across half-life problems and you have to do a bunch of them, it might be. But I just point out we just derived it essentially here. So that means that if we're continuing along solving our differential equation, we now know what k is. It's ln of 1/2 divided by 5700. So now my differential equation is y equals y sub 0 e to the k t, but k is ln of 1/2 divided by 5700 times t. And you'll note that we use the base e, but if you use a little property of logs here, or exponents and logs, you get that you can write this as y naught e to the ln of 1/2 times t over 5700, which is equal to y naught e to the ln of 1/2 to the t over 5700. And e to the ln of 1/2 is just 1/2. So this is where in your pre-calculus experience you were probably told that the half-life equation is always initial present times 1/2 to the t over the half-life. Well, this is where it all comes from here, this exploration that we're just doing now, or the derivation I should say. So there is our differential equation. You'll notice the last thing to solve is the initial condition. So we can do that. Let's just see if I can move this all up over here. We can solve that by using what they told us. They said find the age of a sample in which 10% of the radioactive nuclei present have decayed. So actually we're not interested in the solution to this differential equation, just that particular question. So find the age of a sample in which 10% of the radioactive nuclei originally present have decayed. Well, if 10% have decayed, that means 90% remain. So that must mean that 90% remain. So 90% of the initial amount present, 0.9 y sub 0 equals y sub 0 times 1/2 t divided by 5700. These, of course, go again. And now our goal is to solve for t. So I got 0.90 equals 1/2 to the t over 5700. Let's take the natural log of both sides. So ln of 0.90 is equal to ln of 1/2 t over 5700. And by property of exponents, that can move down, giving me ln of 0.9 is equal to t, oops, forgot the 5 there. It's getting a little sloppy here. This pen is too thick. T over 5700, ln of 1/2. And solving for t, I'll just do that in one. Solving for t, you get ln of 0.9 over ln of 1/2, and all that times 5700 is our t. And if you put that in the calculator, you end up getting t equals about 866.417 years. So that's how long it would take. That's how long it would take for 90% or of 90% of the initial amount to remain, or 10% to have decayed.